which is going on right now. So the whole objective of this paper is to treat this issue of overconfidence that deep neural networks have. So this is a quote from the paper. The model should know what it does not know. So what that means is that the model should not only be accurate, but it should also indicate when and how likely it is to be wrong. So this is an example. Even though modern DNNs are very accurate compared to something like Lenet, so this is like a problem which we're facing today. So Lenet on CFAR 100, so you can see that the average confidence. So one way to look at confidence would just be just to see what is the output of the softmax layer. So once you see the output of the softmax layer, that is that is like an estimate for the confidence of your for your prediction. So if you see that the average confidence and accuracy are pretty close by, which means that like your confidence is your confidence is also a good representation for what kind of accuracy you're getting. Whereas with something like ResNet, which is an example of a modern DNN, your accuracy is much lower than your average confidence, which means that your models essentially have an overconfidence issue. So this is something that the paper it is trying to deal with, and it's trying to fix. So past approaches to deal with this problem. So there's two perspectives with which you can like try to approach this issue. The first one is confidence calibration. So for confidence calibration, what you try to do is that you try to directly output what you think is the true confidence level. So basically, you want to make changes to your model such that the essentially the output from your softmax layer gives you a good estimate for the true confidence level of your prediction. And the second is something called ordinal ranking, and the method given in this paper focuses on ordinal ranking. And what ordinal ranking does is that instead of directly trying to give you the probability, give you the correct confidence level, it tries to rank the confidence levels and the confidence levels of various samples in the batch. So in other words, it's the problem of ranking among samples to distinguish correct from incorrect predictions according to the confidence estimates. And if you want to look at this mathematically, you can look at this where kappa of p, which is your probability distribution, given one sample xi and its weights, is less than equal to kappa of for another sample if and only if the probability of a sample of the first sample being correct, like you making the correct prediction for the first sample, is less than equal to the probability of you making a correct prediction for the second sample. Which means so essentially what it means is that your confidence is directly related to the probability of you predicting that or correctly on that one sample, which intuitively makes a lot of sense. So basically there's been other work on this problem as well. Like you have a lot of Bayesian methods and non-Bayesian methods as well. So like things like MCMC and variational inference have been used. But the problem with these methods is that they're usually computationally expensive for very large neural networks. And there have been Bayesian methods which can deal with the computationally expensive part of it, but they still need multiple forward passes for inference. So the method that's presented in this paper, which is called confidence-aware learning, is simply it's simply an augmentation to the loss function, which basically means that you can get done with this in one forward pass while it not being very computationally expensive. So this is the hypothesis is what the whole the whole paper is based upon. So the authors hypothesize that the probability of being correct, like making the correct prediction, is roughly proportional to the frequency of correct predictions while you during training with SGD based optimizers. So if you look at this, if you look at something like this, I think this is CFAR10. Yeah. So uh, if you look towards the right, so this the x-axis is basically correctness, which means so they trained the model for 300 epochs, and out of 300 epochs, these are in green are the number of are the number of examples in your data set which were correctly predicted at 300 out of 300 epochs, which is a very large portion. And towards the left, you can see that these are the uh, these are the examples in the data set which were wrongly classified around 100 to around 100 times. So these the ones which were correctly predicted, they found that these are also examples which are very, very easy to classify by eye. So if you look at these examples, it's very clear to see that this is an airplane and this is a truck. Whereas for examples which were hard to classify, like even by eye, they are actually pretty hard to classify. Like it is not easy to classify that this is a frog. It could be a lot of other things if you look at it carefully. So they incorporate this concept that like you have easy to classify samples and hard to classify samples in the loss function. And this will also explain why this method is an ordinal ranking method and not a confidence calibration method. So they define something called the correctness ranking loss, which is basically so if you're given two samples, xi and xj, it's basically equal to the max of 0 comma minus g of ci comma cj. So ci would be the proportion of correct event predictions of xi over the total number of examinations. So let's say let's say while you're updating, you go through all the examples in your data set or in your mini batch, and you look at like in suppose you're training it for 300 suppose you're training it for 300 epochs. You look at how many times you got that sample correctly predicted. So it's that, and this function g is basically 1 if ci is greater than cj, which means that if you predicted one sample to be correct more number of times than the other sample, then g takes the value 1. If the number of correct predictions is equal, then it's basically 0. And if you notice, then if ci is equal to cj, this term in the modulus is also 0, which means that the loss is basically 0. What this means is that if you have two samples which are on the right edge of this figure, where you're predicting correctly more or less all of the time, then this correctness ranking loss is basically 0. And it's -1 otherwise, which basically comes back to the first case, just flipped. And then you define the total loss function as just cross entropy loss plus lambda times this correctness ranking loss. So and where lambda is just some kind of scaling factor to influence CRL. So that's since you're using two samples to compare, like between CI and CJ and KI and KJ, this is where it makes sense that it's an ordinal ranking method. And basically what this whole equation means, so this CI minus CJ term in the modulus, basically what you're trying to do here is that the more the gap between CI and CJ, which means the more number of times you've predicted one example correct as compared to the other, the more is the influence on the model. So the more you learn from samples which are very, very different from each other. So that's the whole reason for the CI minus CJ term over here. And so kappa I and kappa j here are basically just this confidence function that we looked at up here. So k of pi given xi comma w would be kappa I, and k of pj given xj comma w would be kappa j. And this kappa can be so this kappa is basically a confidence function. So this could be something like the output from your softmax layer, or it could be negative. It could be negative, and it could be negative entropy, which is normalized between 0 and 1, or it could be the margin, which is basically just the difference between the confidence for the your confidence for the most likely and the second most likely predictions. So that's all for the theory behind the paper. So coming practically to how it works and what people and what they do to make it computationally feasible. So technically, what you should be doing is that the CRL loss should be computed over all sample pairs at each model update, which means that you look at the whole data set. But to make it computationally feasible, they only do it over each mini batch at model update. And yeah, so for the confidence function K, authors consider three simple functions: maximum class probability, normalized negative entropy, and the margin. Margin is basically the difference between the most likely and second most likely predictions. So for the experiments and the results, so the authors basically have conducted a lot of experiments with like a large variety of models. And so for the metrics, the AURC is area under risk coverage curve, which is this. The EAURC is just excessive area under risk coverage curve. NLL over here on the right is just the negative log likelihood, and like they use a lot of metrics for this as well. And overall, you can see that their method, which is CRL softmax, basically does achieve state of the art in a few places. So it's at least competitive. And another pro is that it's very much computationally feasible compared to the other methods. So they also conducted experiments on out of distribution detection, and they've also conducted a few experiments on active learning. And all these tasks are actually very intimately related. So some thoughts on the paper and some questions which I would have had was that, considering the fact that the application of the technique, like the application of the techniques presented in this paper are geared mostly towards safety critical applications. What I mean by that is when it comes to toy data sets like CFAR10 or things like that, you wouldn't be concerned too much about like how, like, if you have this overconfidence issue, because all you care about over there is getting the prediction correct and getting a high accuracy. But this becomes very important when you have safety critical applications like autonomous driving or computer aided diagnoses, things like that. So over there, where the risk of having a false positive is very very bad, uh, I feel like they should have conducted experiments on real world data sets in place of standard data sets that would actually show if the methods presented are useful. On the flip side, they have conducted a lot of experiments, although these are all on toy data sets and they're all on modern DNNs. And yeah, the technique is computationally much cheaper than its predecessors, and it's also very simple to interpret and implement. The idea is very simple. And another good thing is that the proposed technique is model agnostic and task agnostic. You could use this kind of approach to not just image-based data sets and convolutional networks, but you could very easily implement this for language tasks, for audio-based data sets and tasks, or anything like that. So yeah, that's it.
Yeah, I had a question. So when it in the loss you have the CI and the CJ terms, right? And those are basically the proportions of
CI and CJ are the proportions of how much a sample was predicted correctly during training.
so that is during the past, like during the past epochs. So
Yeah, so
it can
basically you
be a bit
keep it
better.
updated while you're going.
Right, right. And so what you're basically trying to do is you're trying to learn these kappa functions, and then trying to
Uh,
minimize the.
no,
Uh,
you're not learning kappa. Kappa is something you select. So kappa, in the most simple case, kappa would be the output of a softmax layer.
okay.
Anything else?
And is this like the how are you choosing xi and xj? Like I didn't understand that part.
Oh, XI and XJ. So you basically go through all pairs of
Okay,
examples in your mini batch.
okay, okay. You
And
sum over all the pairs for the total loss for
yeah,
that
yeah,
batch.
lambda into sum over all the pairs.
Okay, so okay, fine. Can you explain that the mod ci minus cj part
So
once more?
yeah, yeah. So for example, let's say I have. So let's look at this figure. So let's say I have xi, which is on the rightmost of this thing. So it's very very highly probable that you'll predict it correctly, and xj is somewhere on the left end of this figure of this graph. So
Yeah,
like somewhere in this red region and somewhere in this green region. So for an example like that, as you keep training, ci minus cj will be a very large value,
yeah.
which will if
Increase the loss.
yeah, it'll increase the loss over zero if this. So basically you're trying to enforce this condition,
Hmm.
this
Yeah,
kappa. Yeah, so you're trying to enforce that condition. So if you see, then only if this margin, this absolute term is high, will this loss value be somewhere above zero.
yeah,
So this minus g term will always be something like 0 point something, because g of ci comma cj will not be greater than 1 or minus 1,
yeah.
and kappa
Hmm.
I minus kappa j will always be a value between 0 and 1.
Yeah,
So
yeah. Correct.
the more the difference in ci minus cj, the more will be the loss.
Yeah. Okay. Cool.
Anything else?